first in a
Hang on.
Hi everyone, and welcome to the first in a series of academic debates hosted by Intel. We at Intel really value the collaboration and relationship with the academic community, and we wanted to create a platform to host these kind of conversations and debates looking at the trends in hardware security. I'm Amita Lazari. I'm Director of Global Cybersecurity Policy at Intel Corporation. I'm also a lecturer at UC Berkeley School of Information, Master in Cybersecurity program, and I'm thrilled to join you today for this debate. We got some fun session planned for you for the lunchtime entertainment. We invited two fantastic security experts to join us for a lively debate. And our debate is going to focus on a really interesting question. As the industry works to build more safe, more secure technologies, we are faced with limitations, limited time, limited funding, limited resource. In the face of these constraints, we asked our academic experts, what method of security assurance best identifies flaws, security vulnerabilities? If you could pick and choose only one weapon from your arsenal of tools, which would it be? We have challenged Professor Cynthia Storton of the University of North Carolina at Chapel Hill and Professor Thorsten Holz of Ruhr University Bochum to present their best arguments and convince us of their respective technologies. Cynthia says formal verification is your best bet, and Thorsten believes fuzzing deserves all the glory. Over the next half an hour, they will work to convince you of their argument. It should be a fun dialogue, and we encourage you to submit your questions or comments on the Q&A window we opened. We will be opening up the session to audience questions at the end of the debate. But first, let's see where we stand. Let's start with a poll to see where you, the audience, believe we are. Please participate in our poll as we continue throughout this debate. With that, let's get to know our debaters. So, Cynthia Storton is an assistant professor and a Peter Searcher Brewer Fellow at the University of North Carolina at Chapel Hill. She leads the hardware security at UNC research group to investigate the use of static and dynamic analysis techniques to protect against vulnerable hardware designs. Her research is funded by several NSF awards, the Semiconductor Research Corporation, Intel Corporation, a Junior Faculty Development Award from the University of North Carolina, and a Google Faculty Research Award. Not only that, she was recently awarded the Computer Science Department Teaching Award at the University of North Carolina. With so many awards to her name, we asked Cynthia, who is currently quarantining at home with her 10-month-old daughter, and what honor and award she is going after to win next. Her answer, the award of enduring extreme sleep deprivation, but not necessarily with grace. Aren't we all experiencing that these days? Cynthia received her BSE from Arizona State University and her MS and PhD from the University of California, Berkeley. Go Cal, a fellow grad. I appreciate that. We are thrilled to have her joining us today. And on the other hand, facing off against Cynthia, I would like to introduce you to Thorsten Holz. Thorsten is a professor in the Faculty of Electrical Engineering and Information Technology at Ruhr University Bochum, Germany. His research interests include technical aspects of secure systems with a specific focus on system security. Currently, his work focuses on reverse engineering, isn't that fun, automated vulnerability detection, and studying the latest attack vectors. Thorsten received his undergrad in computer science from RWTH Aachen, Germany, and his PhD from the University of Mannheim. Prior to joining Ruhr University Bochum in 2010, he was a postdoc researcher in the Automation Systems Group at the Technical University of Vienna. Furthermore, he is the co-spokesperson of the Cluster of Excellence CASA, Cybersecurity in the Age of Large-Scale Adversaries. Now, these days, you're likely to find Thorsten quarantining with his family, nagging his daughters to clean up, and Hashtag drinking at home. Cheers for that, Thorsten. Thank you both so much for your participation. We are really excited for this debate. We are welcoming our audience participations and questions. And without further ado, I will turn the floor over to Cynthia for opening arguments.
Thank you, Amit. So the question we are considering here is, if your security validation can be done using only fuzzing or only formal verification methods, which do you choose? And I will argue in favor of formal verification. To be clear, I'm not arguing that fuzzing has no role to play or cannot be a valuable contributor to your security validation effort. Merely that if you have to choose one, formal verification is the better choice. Okay, so let me begin by defining some terms. First, fuzzing. Fuzzing is a technique of providing random inputs to a system to see if the system will crash or hang. The technique has evolved and matured since those first corrupted inputs over a static modem line in the middle of a storm. And so now they're really very sophisticated methods that are used to choose the inputs wisely to maximize code coverage. But the goal remains the same. You want to find inputs that the system does not handle gracefully and for which the system either crashes or hangs. And some of those inputs will point to vulnerabilities in the design, points where an unexpected input can lead, for example, to the program executing invalid instructions or instructions stored at some unexpected location. Okay, next, let me define formal verification. And here's the thing, formal verification is not a single technique. It's an umbrella term that encompasses a variety of techniques that includes theorem provers, model checking, type systems, and symbolic execution. So at heart, formal verification is a mathematical reasoning about or an exploration of a system. Formal verification methods are not about looking for specific inputs of interest. Rather, they use a mathematical description of the system along with a formal statement of the desired policy or properties. And using logical inference, proof by induction, and SAT solving, they demonstrate that the policy is true of the system or find flaws in the system that violate the property. Okay, and formal verification is powerful. Reasoning mathematically about a system allows one to, for example, prove that an operating system adheres to its specification, that it has no bugs, and provides strong properties of isolation. Or formal verification allows one to develop languages with well-defined semantics and provably correct compilers, so that the behavior of the system can be fully understood. Or you can use formal verification to explore a code base to find instances where bounds are not checked or not checked correctly, and understand exactly the set of inputs and the path through the code that can lead to an array bounds violation. Okay, but when one hears the term formal verification, I think examples like SCL4 are the ones that most immediately come to mind. These are systems employing heavyweight formal verification methods with complete proofs of correctness. These systems demonstrate the power of full formal verification. And for security considerations, having systems that are guaranteed to be correct, guaranteed to be without any bugs, that's a win. But these kinds of examples are also subject to two of the common criticisms of formal verification. So the first is that there's really a high overhead in setting up your formal verifier. You have to set up a model, develop the properties, improve the properties, and all these things are time consuming. And people will say formal verification is all well and good if your system is small and you need strict security properties of isolation, and you've got all the time and resources in the world. But in the real world, for a practical system, that's just not realistic. I just need something that will find as many bugs as possible, as quickly as possible, and I don't have time for elegant proofs. And the second criticism that is often lodged against formal verification is that the resulting system might be provably correct, but that doesn't mean it's secure. It's bug-free and it adheres to its specification, but there's no guarantee that the specification is correct. So in other words, the verification does not mean validation. So all that work, and you might still have exploitable vulnerabilities in your system. And these are valid criticisms of formal verification, but they miss the real power of using formal verification. So don't forget that formal verification refers to a range of techniques, some of which are heavy duty, but others are more lightweight. A symbolic execution engine can explore native code. Type systems are built into the languages that you use. And what they all have in common is that they involve a mathematically sound comparison of the system to a set of desired security properties. And that is what I see as the real power of formal verification, developing those properties. So in the act of developing the properties that you want for your formal verification, the act of doing that forces the designer to think about the security policy that they desire, developing those properties and analyzing any of the found violations of those properties can help the designer to understand both the behavior of the design more fully and more completely, and also the desired security properties themselves. A counterexample when one is found, if one is found, violates an actual security property. So you already know if a counterexample is found, a violation is found, you know it matters to security because you know it's violating a property that you have laid out as critical to security. If changes are needed, the designer is starting from a point of understanding what is already there, what is true of the system, and where the system has gone wrong. Finally, formal verification can handle properties beyond crashing or hanging, right? You can, using formal verification, you can state properties that are simple safety properties, but also more complex properties, properties about determinism, about non-interference, properties about speculative non-interference. So for example, instances of Spectre-like attacks would not be found by fuzzing alone, but they can be found by formal verification methods. So the goal of our system, the goal that we want is secure systems. We want our systems to be secure against that inevitable attacker, both today and also going forward in the future. And I think we also want more than that. Given that today, with all the tools at our disposal, the safe bet is still on the attacker. We continue to have 0 days. We continue to find new exploits in our most mature, well-tested code. Attackers continue to find a way in. It's naive to think that any given system is perfectly secure. And certainly, I would never trust a product that told me it could detect and prevent all future attacks. So therefore, we demand more from our security teams. We want them to find all the vulnerabilities they can, yes, but we also want them to be well-placed to react quickly to the next 0 day when it does happen, despite our best efforts. And for that, I want a security team that understands and has the tools to examine not just the system and how it works, although that is the first critical step and formal verification helps with that first step, but also the security ramifications of any given patch, for example, or how components might be reorganized or better composed to strengthen the security of the system overall. And for that, a security team with the tools and experience to harness the analytical power of formal verification gets my vote every time.
Okay, so Cynthia has raised some really interesting arguments. And with that, I am very curious to hear Torsten counter arguments and rebuttal. So Torsten, let's give you the floor and please tell us all the arguments that you have for fuzzing.
Thanks a lot, Amit, and thanks a lot, Cynthia. So actually, you almost convinced me that formal verification or formal methods is the way to go, but at least I have the audience behind me, 40% for fuzzing, and I hope to convince even some more people that fuzzing is the weapon to choose in case you want to find bugs efficiently. But first of all, I need to state that I really appreciate the arguments by Cynthia. I really appreciate formal methods as a computer scientist because it's an elegant way to analyze a given system. So we have a wonderful theory, we have formal proofs, so we have actually a fine line of reasoning why specific properties of a system hold. And in case our methods basically turn out that a specific requirement does not hold, then we even get some kind of counter argument. So typically some kind of input that tells us, okay, if you provide this input to the given system, then this type of crash happens. Or you can also formulate other kinds of properties that you want to hold. For example, let's say you want to analyze a smart contract. You could also formalize this as after the attack has happened, the victim contract has more ether on his contract than before the attack. So you can actually have a nice way to formulate arbitrary kinds of conditions. So it's a wonderful approach. And we have also wonderful tools in that space with SEL4. We have a formally verified operating system kernel. We have with ComCert a compiler. We have CLE as a symbolic execution engine. So lots of interesting tools. And as I said, Cynthia, you almost got me. But then there are, of course, also some drawbacks. And I want to talk about a few of them. Probably there are more, but for the sake of time, with my 10 minutes, the first thing that I typically complain about is scalability. Because with formal methods, you can typically analyze smaller programs, which I mean tens of thousands, maybe hundreds of thousands of lines of code. But in practice, the modern software stack are much bigger. So a web browser has probably 20 million plus lines of code, or just here the video conference that we are doing, just the video from my room to your room probably requires many, many million lines of code being executed across many types of systems. So we have actually quite complex systems these days, and this is actually one of the main drawbacks of formal methods. And actually, that's a long-standing problem in that space. I remember when I was a first-year PhD student, I attended a workshop where formal methods people basically came together. I just attended the workshop just for fun. And then at the morning of the second day, there was a keynote by somebody from SAP, so one of Germany's biggest software companies. And in the keynote, he actually complained about symbolic execution and all the formal methods. And then actually it turned out that this 45-minute keynote turned into a 2.5-hour discussion, because also the formal methods people, of course, couldn't agree with his arguments. And it was interesting to see this as a first-year PhD student, how this academic discourse actually looks like. Then my second main criticism is that within formal methods, you typically need to describe some kind of attacker model. So you need to build up some kind of requirements, some kind of theory behind all of this. But in practice, actually attackers try to break the rules. So they try to do things that you do not expect. They think outside the box. They do things that you have not anticipated before. And by doing so, they compromise the system. So they find this one way that you didn't think about. And there are actually some studies that analyze formally verified systems and still find software vulnerabilities in them, given that all this nice theory, all these things that you've built in your formal model are at the end some kind of abstraction. They do not actually model the real world, but the real world is always a bit different. So imagine something like SEL4, where we have a formally verified operating system. But if we then run this on top of a commodity CPU, then we have all this type of side channel attacks, or we have something like Rowhammer, Spectre, Meltdown, and all of them. So in practice, the attacker takes advantage of something that you didn't model in your system, and then he can bypass some of your defenses and eventually compromise your system. Or to take up one of the arguments by Cynthia, that basically with formal methods, you can find Spectre-like vulnerabilities. But then, of course, my question is, if you can find this, why didn't the whole thousands of people working in formal methods didn't find Spectre-like vulnerabilities before they were uncovered by the researchers a few years ago? So after the fact, of course, you can model this. You know what the attacker does. You can formally model your system, and then basically find interesting or new instances of Spectre. But without knowing how a specific attack vector works, it's actually pretty hard to do this. And then I'm arguing why to work on fuzzing. So why to basically pick fuzzing as your tool of choice. But first of all, I need to say that fuzzing is raw. Basically, it's not elegant. It's basically just sending random inputs to a program and hoping that eventually something interesting happens. Of course, that's a bit too simple. I think today we have a better understanding why fuzzing works, but still it's only a glimpse into why this actually works, why it is effective. We have no real theory behind it. I think this is still an open research problem, but still in practice, we see that this is actually working quite well, especially because fuzzing is basically brute force. And if you can execute a program 1,000 times per second, then you can actually get quite a few million executions per day. And you only need to find this one single input that basically leads to a crash and you're successful. You can parallelize this easily, so you have basically a good way to spend your computing resources. And we see that large companies like Microsoft, like Oracle, like Google are actually spending tens of thousands of CPU servers, tens of thousands of servers just on fuzzing, because they have the raw computing power, and they find tons of bugs these days. Especially coverage-guided fuzzing, which was pioneered by AFL and then later refined by tens or hundreds of academic papers and lots of industry work, actually is at the moment the way to go. So we've seen a lot of innovation in that space recently. We've seen that we have basically many tools available, and we can cover many aspects of the system stack. So we can easily fuzz user space programs, we can perform fuzz testing of operating system kernels, of hypervisors, of embedded systems. So we can basically fuzz different types of systems, and this is done in a more or less generic way, in the sense that once we have a framework, let's say we have an operating system fuzzer or we have a user space fuzzer, we can plug in arbitrary OS kernels or arbitrary user space programs, and then just let it run and eventually find the bugs that we care about. We can even perform fuzzing of more complex systems. Just as a teaser, we have a paper at this conference that will be presented on Wednesday, where we show a way to fuzz Super Mario, so a game, and we can actually fuzz a way through the game levels, and Mario will eventually find the princess. So nice demo of us. And Wednesday, you can learn more about this. And we have more and more integration these days. So there are, for example, some startups that enable you to integrate fuzzing into your continuous integration environment, such that during the development, you can already do fuzz testing. We have many startups working on fuzzing, let's say, for example, on embedded systems, or just add it to your tool set. So lots of innovations, both in academic and also in industry. We see the big players picking up this technique. And in the practice, things like syscaller, which is basically an OS kernel fuzzer, found thousands of bugs, or tens of thousands of bugs, even in Linux or Android. And if you compare this to the bugs found by formal method tools, I think you're probably orders of magnitude less. No offense, but I think fuzzing is the way to go these days. And others also support my argument. And as a final statement, if you take a look at the DARPA Cyber Grant Challenge, where basically DARPA put millions of prize money into building tools to find bugs, actually the 6 teams that went into the final, all of them picked fuzzing as the tool of choice to find vulnerabilities in the first place. Of course, I need to say that also some integrated fuzzing with formal methods. So at the end, it's not black and white, but it maybe is some kind of combination of both. But all the teams picked fuzzing as one of the building blocks to find actually vulnerabilities in the systems. And with this, I hope you vote for fuzzing when you need to pick a weapon in the future.
Thank you so much. So we have heard some interesting arguments from Torsten as well. And, I got to share with you all, as some of you may know, probably most of you don't, my doctoral degree is actually in the law. And you fellows are just great litigators, throwing all the arguments out there. Definitely, you should consider the Supreme Court litigation route as well. And with that, we have heard so much. I want to bring it back again to Cynthia and hear from her rebuttal to Torsten's approach. And as a reminder to all of you, we still have the Q&A window going on in the background. Please submit your questions, and we're going to get back to them after the rebuttal.
Thank you, Amit, and thank you, Torsten. Those are excellent arguments. And I agree that fuzzing is an excellent tool, and if we had all the tools available to us, I say yes, we should keep fuzzing around. But if you have to choose one, we choose formal verification. So let me see if I can go through your arguments one at a time. So your first your first point there was basically, even if you apply formal verification, your system might still be vulnerable. There will still be exploitable vulnerabilities in your system, whether it's because you failed to model the attacker correctly, or you just failed to come up with the necessary property to, for example, to know about Spectre and Meltdown-like attacks. And to that, I say, yes, I don't think we've seen a tool that can guarantee a secure system. I don't think we've seen anything out there that says like, oh, here, you build your system and use this tool and guaranteed security. The attacker always gets the last say, and so that always gives the attacker the edge. But with something like formal verification, now that we know that, oh, we should care about Spectre-like attacks. We've known about side channels for years, and certainly formal verification has been used to find instances of side channels, but now we care about Spectre-like attacks, and now we can look for all of the different points in the design of the software and also the hardware. Find all the different points in the design space that are vulnerable to this kind of attack, now that we know we care about it, right? And that's really the power of formal verification. Let's see. So your next argument was fuzzers will find you 10,000 bugs, and formal verification will not find you 10,000 bugs. And that is true. I would say, though, that if I were a designer and tasked with verifying the security of a system, and you came by my desk and gave me 10,000 bug reports and said, here, go, and I want a secure system at the end of the day, that's too much, right? What do I do with those 10,000? How do I triage them? How do I figure out which are the ones that are really critical to security, that are actually exploitable, versus the ones that are like, yeah, not ideal, but I'm not going to handle it right now. So I think 10,000 is the wrong number. We don't want 10,000 bugs. We want a small number of exploits, of counterexamples to properties that we know are critical to security, that we know, if this is violated, this is exploitable. Prioritize this and patch this. I think your final argument against formal verification was this issue of scalability. And it is an issue with formal verification, right? There's definitely work to be done here. The current approach is to decompose, to use assume guarantee reasoning, to find ways to decompose and then recompose, right? So certainly there's research to be done here to continue to push formal verification methods, right? It's not done. The field is not complete, right? But I think it is worth pushing on it in order to be able to apply these methods that are so strong to all of our systems.
Great. So we heard some very interesting rebuttal arguments as well. And with that, I think we are ready for our Q&A and getting some questions from our audience, right? So let's kick off the discussion. We did receive some comments in the Q&A as well, which is very academic as well. Thank you so much for the peer review process, and I welcome our speakers to look at the Q&A on the comments as well. But we also received some interesting questions. So first question I would like to kick us off with is, for both speakers, and Cynthia, we will start with you. What would be your favorite fuzzing and formal framework? So Cynthia, you can argue for formal verification, and Torsten, you can comment on the fuzzing, that you would recommend practitioners new to the methodological kind of relaying to first try, and why? So from the arsenal, pick one, either fuzzing or formal framework that we would recommend specifically for practitioners to try out as a method for the first try.
Okay, well, I would say, formal verification is really this umbrella term that includes so many different tools. So I would say, first I would just remind you that if you're using typed languages with strong typing, that already you're using some formal verification. If you're looking for something, some external tool to evaluate your system, in my research, have been using symbolic execution a lot, and I think that has, of the tools available, that has a pretty low barrier to entry for new people, new to formal verification. So symbolic execution is pretty close to plug and play, with native code. And you can explore your code and find some really valuable, some sort of valuable, properties, or find violations of valuable properties in your code.
On the fuzzing side, actually quite a lot of tools have been published recently, and I would recommend to take first a look at AFL++, which is a tool set that combines AFL, which was basically the prototype of coverage-guided fuzzing, and adds some other fuzzing techniques that were published in different types of papers. And AFL++ is basically an easy-to-use framework for fuzzing. And I think it's a good starting point just to get used to the tools, and you can easily play with it, get different kinds of fuzzing techniques up and running. And then the other starting point could be that Google recently released a fuzzing benchmark framework, where Google is actually running a number of different fuzzers on different kinds of programs, and they give some kind of performance numbers of how these different fuzzers performed on these different types of programs. And there you see that also, depending on the program, some fuzzers perform worse or better, but still AFL++ is probably a good starting point for playing with the tools.
Okay, thank you for that. So we are getting a lot of questions. Here's a quick one. Abstract interpretation was raised here as a light fuzzing verification tool. What's your take on that?
Okay, so this question is just that also you can end up with many thousands of warnings, and it can be overwhelmed by these as well. Yeah, and I would say even there are many tools, so some have some strengths versus others. And I'd say even beyond this question, right, I think it is fair to say that formal verification also, there's work to be done to make it more usable, to make it easier to use. And that's both like the input to the tool and also handling the output and reading the output. So there's definitely some more work to be done on this side. More different techniques will give you better and worse results in terms of highly prioritized results.
Okay, and again, on the interaction between those tools, it's, in reality, it's not either or, right? But for the purpose of this debate, we wanted to frame the question like that. And one of the interesting questions that came in, the speakers, maybe you can comment on this. A member of our audience is saying, Cynthia, you said there is research to be done for formal verification. And Torsten, you highlighted that fuzzing is already in use today, and attackers are actively using fuzzing. So why would defenders lag behind attackers? So I think this is a question about the tools that are being used by attackers versus the methods and tools that are in the arsenal for the defenders. I don't know if you have a comment about that.
Yeah, formal verification is also currently in use today. The fact that there's research remains to be done doesn't mean it's not already being used. I would argue there's research that remains to be done with fuzzing as well, right? Formal verification is already in use today. One thing is with formal verification is that the developers of the code, formal verification is a white box technique. Basically, most often you need the code, right? And so developers of the code have this tool in their arsenal that it is more difficult for attackers to use because they first need to reverse engineer the code or get their hands on the code if they don't already have it. So the fact that attackers are using fuzzing, I would argue one reason maybe is that it's easier to use fuzzing on code for which you don't have the source code, whereas the developers are already using formal verification techniques, and I am sure they will continue to do so, which is why there's a lot of funding for this kind of research.
Yeah, I completely support this argument. So formal methods are huge in practice. We wouldn't have a single airplane without, or any type of avionics without formal methods, or in cars or many other types of security critical systems. Actually, formal methods is the way to go. I would see that fuzzing is probably used in practice by attackers more, given that it's really easy to use. So basically you have your command line tool, just start it against the target that you want to fuzz, let it run, and then hopefully within a few days or a few hours, maybe even, you find the first crashes, then you need to analyze what's actually happening. And you do not need all the modeling and everything before, but you basically take something out of the box, just let it run, and then hope that eventually it will find something. So ease of use is a bit better for fuzzing compared to formal methods.
Thank you so much for your perspective. And here's another interesting question, and I like it because it's about collaborating between the approaches and maybe getting to some kind of mediation in our debate and argument. So the question is, are there tools that combine, formal verification with fuzzing that you can either define, a fuzzer objective in a model logic such as LTL, and the tools generates not just a counterexample, but also an easy to interpreted trace in a formal syntax. So what can you kind of outline for us as kind of future combinations of those kind of these two different approaches?
Mm-hmm. Maybe I can start to answer this question because, of course, my arguments were a bit opinionated. This is a debate that's your lunchtime entertainment, and for me, it's 9 or 10 p.m. already. So we try to exchange arguments here. And in practice, actually, there are some ways how this can be combined. For example, fuzzers like Driller or QSIM, they first perform the fuzzing, and then whenever they find an instance of some kind of condition that via sheer brute force they cannot actually solve, then they fall back to some kind of formal methods, for example, to symbolic execution, and then basically try to set up a formula from the beginning of the program to the condition that they cannot solve, and then use an SMT solver in order to find an input that satisfies this one constraint in order to bypass it. So whenever brute force doesn't help, they try to integrate formal methods in order to help out. And this works actually in practice for many cases. So QSIM has actually good performance, although again, scalability to real complex systems is an issue. But still, combining both methods is actually worthwhile, and I think that's also a promising area for future research.
And I'll just add to what Torsten said. In hardware verification, there's assertion-based verification where you design the properties that you care about, but then you can use testing basically to find violations of those properties. You can use something like symbolic execution, but also simulation-based testing is used. And for that, you want a good way to generate inputs, and it gets very similar to what's happening with fuzzing, right? So that, again, is this combination of the formally stated properties that you care about. You can add them to your design as assertions, and then, run the system with a lot of inputs, some well-chosen inputs to see if you can violate those properties. So the two work well together.
Mm-hmm.
Thank you so much. And there are many questions we didn't get to, but I'm sure our debaters will look at the Q&A window and they definitely spark some thoughts. With that, each of our speakers, 10 seconds by, your one big takeaway for our audience. Cynthia, go.
Formal verification methods help you understand your system.
Torsten?
And for fuzzing, if you just want to find bugs easily, just pick a fuzzer.
And for me, I think, what's really is kind of an underlying arch across this discussion is we value so much this kind of dialogue, this kind of collaboration, and it's clear that the research to tackle future challenges in security is going to continue and be a priority, and I'm very grateful for this platform. I'm very grateful for the debaters today and their time. Thank you so much for our speakers, bringing together all these interesting perspectives to the table and engaging in this debate. And I would like to thank our speakers, our audience, everybody here in IEEE SMP for the platform. Thank you so much, and enjoy the rest of the conference.